Hello, today we're going to be looking at the Doppler effect. It's in physics, and it's a really cool phenomenon that we all experience in the real world. So it's better to demonstrate this visually, and so there is a visualization on Cognigy that shows this. So let's look at this. There are two observers, two humans in this case. They're stationary, and there is a source that is producing waves. Let's say this is sound waves, and this wave, the source is moving from observer A to observer B at a constant speed. So let's look at what happens. The waves that observer B is experiencing, let's look at this again. They are more compressed and the wave fronts are more compressed. They're more together compared to observer B. And it just intuitively makes sense because it's moving right. And so the wave speed is the same, but it's producing a wave more to the right as time passes by. And so this just intuitively makes sense when you see this illustration. And the cool thing that this does is, so if this is a sound wave, so we know that this formula exists, F lambda. So V is the velocity of the wave, F is the frequency of the wave, and lambda is the wavelength of the wave. So let's look at this. We can see that because the wavefronts are shorter for observer B, but longer for observer A. We can see that it's because the distance between the wavefronts is the wavelength. So we can see that wavelength is the variable that's affected, that's changed here. And the velocity of the wave speed is the same. So we can say that, first let's isolate frequency actually. Okay, V over lambda, and velocity is the same. So frequency is proportional to 1 over lambda, or frequency is inversely proportional to lambda. So this means because observer B is experiencing wavelengths at lower wavelengths that are shorter, while A is observing wavelengths that are greater. For B, since wavelength is decreased, that means frequency increases. So in this case, observer B is experiencing a frequency of sound that is increased, whereas A is experiencing a frequency that is decreased. And this is very interesting because the frequency of the source is the same, but it's because that it's moving that the frequency is different. And therefore we know that for sound, a higher frequency means a higher pitch. So that means for observer B, they hear a higher pitch compared to A. So even though it's the same sound, they're not experiencing the same sound, and this is because it's moving. And it's just, I find it very interesting how this happens in the real world, and this is essentially the Doppler effect. It's the same sound source, but because it is moving, people experience different pitches or different sounds, essentially. Okay. There is another case where, let's see, where it's like this, and in this case the wavelength is the same for both. However, the wave speed is different. And so if we isolate, let's see. Yeah, so this just, and because wavelength is the same, that means lambda is the same. So it's just frequency is directly proportional to the speed of wave that they're experiencing. And so because observer A is moving towards the source, they're experiencing faster waves. So faster waves means higher frequency, and higher frequency means higher pitch. So once again, even though it's the same sound source, because they are moving either to or away from the sound source, they are experiencing different sounds. And once again, I find this very interesting. You guys should too. Okay. Now, okay, another phenomenon you guys have probably all seen is a jet breaking the sound barrier. And this is essentially when the jet is flying faster than the speed of sound. And we know that the speed of sound is around 340 meters per second. And so when a jet is flying faster than this, it's considered to be supersonic. And let's just visualize this. Let's say the jet is right here, and this is essentially what it's going to look like. All of the waves are building up because it's moving, almost like, in this case, it should be moving exactly the speed of sound so that all the waves that are produced are equal to each other. And this part right here, there's a lot of pressure built up there, and once a jet flies faster than this, it breaks this pressure and it creates that large sound that you hear when a jet breaks the sound barrier. And the interesting thing is when it travels faster than this, it looks like this. And this is what they call the sort of cone shape, because it looks like this. And so the jet is like right here, let's say, right here. And the interesting thing is when you, so let's say if you're here and the jet is flying this way, the interesting thing is because the sound waves are going to be all behind the jet, that means theoretically you shouldn't be able to hear any of the sound made by the jet until it passes you right there. And if you search up videos online, you will be able to see that this is the case. You won't hear a jet flying supersonic until it passes you. And that's just, I find it very cool. So this is just the Doppler effect, and animals actually use this natural phenomenon. They use the double Doppler effect, including bats and dolphins. So you guys have probably heard of echolocation, that these two animals use it. And what exactly is echolocation though? So that is when, because waves, you guys have probably shouted before in a garage and heard the echo, some sort of echo, and that's the sound wave bouncing back from whatever boundary it hit. And so let's say the bat or the dolphin is right here, and it produces sound waves, and there's a wall right here, or an animal or a prey. And once it hits here, it's going to bounce back, essentially. And the interesting thing is they use the Doppler effect to determine the direction, the speed of whatever prey or whatever object that they're tracking. Because let's think about it this way. If the animal that they're tracking is moving this way, once the waves hit the prey or the animal, it's going to bounce back at lower frequencies than the original one because the animal is moving farther away. And so it's going to take more time than the original frequency to bounce back. And so the bat, let's say it maybe emitted a frequency of 5k hertz, 5,000. And once it bounces back, it hears a frequency of 3 hertz. And so it's going to know that because it's going to hear a pitch that's lower. And therefore it knows that the prey is traveling away from it. Whereas let's say the prey is traveling towards the bat. If it emits a frequency of 5 k hertz, it might come back with, let's say, 10. So it's going to be a higher pitch, and they're going to hear that, and they now know that the prey is approaching them. And they also know the direction too, because it's very specific, it's very complicated, but it's just that if they hear that the sound first met their right ear, it knows that it's on the right. Whereas if they first hear it like a few milliseconds before they hear on the right, so they heard it on the left first, it knows that the object or the prey is on the left. And that's just very interesting, I find. But the thing is, we actually can't hear the sounds made by bats because their frequency that they emit is actually higher than the range of frequency that we can hear, which is like the max that we can hear is like 20,000 hertz, I think, and they do higher than that, so we can't hear it unless we have like special instruments. And for dolphins, we know that they do sort of clicks in water, and sound actually travels faster in liquids and solids because sound is a mechanical wave, so it requires a medium, and so I think it travels like 1,400 meters per second or something in water, so it's even faster than in air for dolphins. So yeah, that's how they use the Doppler effect for practical purposes, for hunting and to get food. And they use a double Doppler effect in this case because it bounces there and then it bounces back. And yeah, that's what the Doppler effect is, and I find it really cool that it just exists and that animals use them, and how a speaker, we can hear different things if we're either moving towards it or moving away, or if the source is moving towards us or moving away, and it's very cool, I find it. Anyways, thank you, and I hope you enjoyed.